In exercise 223, we try to understand more about the stability of a shooting method. And in this exercise, two of the exercises A and D, they ask us to find the exact solution of a differential equation. And in A, we are asked to solve this differential equation using these two initial value conditions. Now, how do we solve that exactly? Because that is what we are asked to do. One way to do that is to write this into some Maple code or SymPy code and then just ask the computer to do the work for you. But since this is a course on finite difference methods for differential equation solving, and that also kind of requires that you know something about differential equations as well, let's try to take a look at how I would solve this equation in an exact manner. Well, the first thing you have to do is to open up a web browser and go on Google. And then a good way to start is probably write something like solve a, and let's just take a look at this equation here. Well, it is clearly a second order differential equation. It is linear and it is also homogeneous. So let's just start off with that. Solve a second order linear homogeneous. Well, Google did the work for me, so I can just do this. I could have also written second order linear homogeneous ordinary differential equation, but let's just try this. And the first thing we get is this PDF file. So what I did earlier when I tested this through was I clicked on this link and it gave me this thing here. And that's very nice because nothing says that you can only use the Holmes book as literature. So let's take a look at what we have here. A second order linear differential equation has this form. Yes, I agree with that. And then it says something about non-homogeneous and blah, blah, blah theorem. And is there anything we can use at all? Here. Okay. In general, it is not easy to discover particular solutions to second-order linear differential equations, but it is always possible to do so if the coefficient functions are constant functions, that is, if the differential equation has the form this. And yay! Because our A is just 1, B is minus omega squared, and C is just equal to 0. And where these are constants and A is different from 0. Okay, and then what do they tell us? Here, okay. So if the roots R1 and R2 of the auxiliary equation A times R squared plus B times R plus C equals 0 are real and unequal, then the general solution of this is given by this thing here. Wow, that was really nice. So the only thing I need to do is to find the auxiliary equation. And, well, what's the auxiliary equation? They call this the auxiliary or characteristic equation of the differential equation. So I have A times R squared plus BR plus C equals 0, and I want to find the two roots of this. And in the case that both roots are real and distinct, then this expression here will be the solution to my differential equation. So let me just try to write that up. So this has characteristic equation. What did they say? A times R squared, so that is 1 multiplied by R squared, and then plus B times R, which is minus omega squared times R, and then plus C times 1, and I don't have any C here, so that's just 0. So this is my characteristic equation. So basically I want to solve this, And that's quite easy to solve. So solve this. Then R1 is equal to some value and R2 is equal to some other value. And when I have found those, then I have that the solution y of x is given by c1 times e to the r1 times x plus c2 times e to the r2 times x. Okay, and where r1 and r2 are numbers that I have already figured out from here. So what are c1 and c2? Well, I can calculate those based on the fact that I know that y of 0, which here is equal to c1 plus c2, because if I put 0 in the exponent, these just become 1, that y of 0 is equal to alpha. And also that I know that y prime of 0 is equal to s. So I can get y prime of 0 by differentiating this once with respect to x and then plug 0 in, and I know that that value has to be s. So based on these two equations, I can isolate c1 and c2 and replace them back into here, and then I will be able to find the exact solution in A. Now, something interesting happens if this characteristic equation does not have any real roots. So let's just go back to the PDF I found on the internet, which is oh so sweet. This is a really, really good book, by the way, that I can recommend. I don't know who wrote it, but it's quite nice. So this smart guy tells me, so there is a third case, right, where I have to consider if the roots R1 and R2 are complex numbers. Then we can write R1 as alpha plus I beta and R2 as alpha minus I beta. And in which case, well, you need to do some work, but then in which case we will conclude that if the roots are complex numbers, then the general solution is given by this thing here. So we should also write that up, but I'm really too lazy to do that, so you can just do the Google work and write this up yourself. And I just might hint that this part will be of relevance in part D. So happy solving, and hope you have a nice afternoon or weekend or day or whenever you're watching this video.